All right, so that brings us to section 11.5, area in polar coordinates. There are actually 2 or 3 different calculus applications in this section. I usually just focus on area. That's the one that you're probably going to find the most useful in Calc 3, multivariable calculus. All right, so I'm going to present this formula to you, and then I'm going to switch over to the tablet and kind of show you a picture of what this looks like. So this is a formula for the area of the fan-shaped region between the origin and the curve r equals f of theta for theta between alpha and beta. So you see that formula here. A for area is equal to the integral from alpha to beta of 1/2 r squared d theta. All right, so now I'm going to switch over to the tablet, show you what that looks like. And here it is. So over here, I've got my curve that I'm calling r equals f of theta. All right, so if you look at a particular range of theta values, this formula gives you the area of this region, okay? Now, there's one other thing I want to add to this. So you remember, currently we cover this at the end of Calc 1 for finding either the area under a curve or the area between curves. Generally, if it's in Cartesian, you do the integral of the top curve minus the bottom curve. Well, in polar, it's a little different. So what I want to show you, I'm going to draw another picture here. So let's say that you have 2 polar curves. One is like this. So we'll say this is r equals f of theta. And then you have another polar curve. Let's say it's like this. And this is r equals g of theta. And you wanted to find the area of the region in between. Okay. And let's say that this intersection point corresponds with the angle alpha, and this one here corresponds with beta. All right, then the area of that curve would be given by the integral from alpha to beta 1/2. You do the outside curve squared. How many parentheses do I need here? Minus the inside curve squared. Okay. So again, in Cartesian, it's top minus bottom. In polar, it's outside minus inside. And remember, you do have to square them. So I'm just going to put a little note here. This is the outside curve. This is the inside curve. Okay. Because I don't think that particular thing comes up in either of my examples. So I wanted you to see that. All right, so let's go back briefly to the presentation. I'll show you the 2 examples I'm going to cover. So we're going to find the area of each region. The first region is going to be the region inside the cardioid, r equals 2 minus 2 cosine theta. And I want to point out, in case you forgot, that we graphed this cardioid earlier. So we already have the graph of that. And then we're going to find the area that is of the region shared by 2 circles. All right, and I'll show you a picture of that. All right, so switching back to the tablet. All right, so what I've done here is I graphed this cardioid on my calculator, and then I've taken a screenshot of it, so we have a really nice picture of that. And notice that you can use symmetry with this one. All right, so here's what I'm going to do. This over here is theta equals 0, and this is theta equals pi. So I'm just going to integrate from 0 to pi, which is going to cover this region here all the way here. And then I'm going to multiply that by 2. All right. I don't know if it'll technically make anything any simpler, but that's what I'm going to do. All right. So the area is going to be, actually, let's do this in red. It's going to be 2 times, because again, I'm only doing the top half, the integral from 0 to pi of 1/2. Oh, let's just write it like this first. R squared d theta. Notice the 2 and the 1/2 cancel each other out, so that's kind of nice. So we're just left with the integral 0 to pi. R is equal to 2 minus 2 cosine theta. So that has to get squared. All right, so now I'm going to multiply that out. The square of 2 minus 2 cosine theta is 4 minus 8 cosine theta plus 4 cosine squared theta. All right, so no problem with those first 2 terms. Hopefully you sort of remember the trick for integrating a cosine squared. You have to use the power reducing formula. So we're going to have 4 minus 8 cosine theta. And now I'm going to replace this cosine squared theta with 1 plus cosine 2 theta over 2. All right, so now I can divide 2 into 4, which goes 2 times. And I guess I will go up here. I don't know what I was thinking. I should have left a blank slide for this one. All right, so what we have is the integral from 0 to pi of 4 minus 8 cosine theta plus, let's go ahead and do this. I'll distribute the 2. So that's going to give me 2 plus 2 cosine 2 theta. Hopefully you can see that okay. All right, so the only thing I can see to do with this is to just combine these like terms. So that's going to give me a 6 minus 8 cosine theta plus 2 cosine 2 theta. We are almost there. All right, so now finally doing the integration, we get 6 theta minus 8 sine theta. And then by baby U substitution, well, actually 2 cosine 2 theta is the derivative of sine 2 theta, isn't it? So this is just going to be sine 2 theta. And now I'm going to plug in pi, plug in 0. And that's going to give me 6 pi. And now this is something I get a kick out of. This happens frequently with these area and polar coordinates problems. So minus 8 sine pi, which is 0, plus sine 2 pi, which is 0. And then when you plug in 0, every single one of these terms is a 0. All right. So the only term that ended up mattering was the very first one. So the area of this region is 6 pi. All right. Moving right along. Okay, so now we're looking at the area shared by the circles r equals 1 and r equals 2 sine theta. So I did not go over the details of graphing this particular curve, r equals 2 sine theta. So that's something that you might want to pause the video and try to work on first. Just convince yourself that that really is the graph of a circle or the equation of a circle. All right, so hopefully you can see that the region we're looking for is this region here. Okay, so the first thing I'm going to do is zoom in on that region. There, I've zoomed in on it. And first of all, notice that I am only looking at the right half of the region. Let me trace this out for you so that you definitely know what I'm looking at here. Okay, so we're going to find the area of this region and then multiply that by 2. All right, so this one is a little bit more complicated. When you do an area in polar coordinates problem, you have to remember that you're always starting from the origin and then working your way out. So what happens in this case, I start at the origin and I go outwards like this. And up until a certain point, I am always exiting the region through the top circle. I'm sorry. So this, notice that this curve here is r equals 2 sine theta. Okay, but that's only true until I get to this point, right? And then everything changes. As I continue through the region, now all of a sudden, I am exiting the region through the other circle, r equals 1, okay? So the moral of the story is that this area is going to be found by doing 2 separate integrals. And this has happened to you before, right? At the end of Calc 1, sometimes either your top curve or your bottom curve changed, partway through the interval. So the same thing is happening here. So I need one integral that's going to give me region 1 right here. And then the second integral is going to give me region 2. Okay. So I will add those 2 integrals together and I will multiply the whole thing by 2 because remember, this is just the right half of the region. So the very first thing I need to do is figure out what value of theta corresponds with that point. And that's just a simple little pre-calc problem. So just like finding the point of intersection between 2 curves in rectangular, you take the 2 equations and you set them equal to each other. So I am going to set 2 sine theta equal to 1, which means sine theta is equal to 1/2. And that means theta is pi over 6, right? Sine theta is equal to 1/2 when theta is pi over 6. So again, the area of the region is going to be 2 times area 1 plus area 2. All right, so what I'm saying to you is that area 1 is the integral from 0 to pi over 6 of 1/2 times, remember this curve was, oops, can't really see that, can you? R equals 2 sine theta. So that's what I'm going to fill in for R. So that's going to go here, 2 sine theta squared. And then the integral that represents area 2 is going to be the integral from pi over 6 to, let's see, how long does this continue? Well, until I get to this point up here, which is pi over 2, right? So that second integral needs to go to pi over 2. And that's going to be 1/2. And this should be a nice easy integral because for that curve, r is equal to 1, right? So that's all you have to do there. Close the parenthesis. All right, so here's something I can do. When I distribute the 2 over both of those integrals, both of the 1/2s disappear, right? Disappears there, and then I distribute it over here, and it also disappears there. So that's kind of nice. So then I am left with the integral from 0 to pi over 6 of 4 sine squared theta d theta plus the integral from pi over 6 to pi over 2. This is just going to be d theta, right? All right, so that'll be nice and easy. And then the first integral is very similar to what we just did in the last example. I'm going to replace sine squared theta with the power reducing formula for that, which is 1 minus cosine 2 theta over 2. And then I think I'll just go ahead and evaluate this one. Why not? So that's going to be theta, plug in pi over 2, plug in pi over 6. All right. So 2 goes into 4 2 times. So we are going to be integrating, distribute that 2. That's going to give us 2 minus 2 cosine 2 theta. And then this over here is just going to be pi over 2 minus pi over 6. All right. And now I finally have a blank page I can go to. So let's go over here. Actually, I think I had better recopy that integral. So we're all looking at the same thing. So that's going to be 2 minus 2 cosine 2 theta. And then I guess over here, I can just write, what is pi over 2 minus pi over 6? It's 3 pi over 6 minus pi over 6, which is 2 pi over 6, which is pi over 3. So we'll just let that sit there. All right, now we can evaluate this integral. The integral of 2 is 2 theta. The integral of 2 cosine 2 theta is, again, sine 2 theta. This time it has a minus in front of it because there was already a minus there. Plug in pi over 6, plug in 0. All right, so we get 2 times pi over 6, which is pi over 3, minus the sine of pi over 3, minus a couple of zeros, right? All right, and what is the sine of pi over 3? The sine of pi over 3 is root 3 over 2. And then when you put these pi over 3's together, it turns out that the area of the region shared by these circles is 2 pi over 3 minus root 3 over 2. So not quite as pretty an answer as we got for the last problem, but that is the answer. All right. Well, we have finally made it. That's going to do it for Calc 2. Congratulations, you made it. Woohoo! All right. Take care, and we will see you another time. Bye-bye.